Yeah, good evening. Let's start the revision session. So, I think there is some problem with the streaming, so I take care that I'm recording the session. We'll share with you the link. Okay. Okay, let me share my screen. Are you able to see my screen?
Yes, ma'am.
Yes, ma'am.
So, before doing some numericals, we can just revise the contents of the 3 weeks. So, we started with the phases in week 1. So, we have the basic four representations for the phaser, that is the polar form, rectangular form, trigonometric, and the exponential form. So mainly we will be dealing with the polar and the rectangular form. So if we have a signal v of t equal to vm sine omega t plus theta, and if I say that the reference signal is vm sine omega t, then the v of phasor representation for v of t in polar form will be in polar form. Generally, unless otherwise mentioned, we consider by convention the magnitude part as the RMS value. So it will be Vm by root 2 angle theta. So this is actually the RMS generally by convention, which is used in the polar magnitude of the polar representation. Okay, generally, rarely you will be seeing it in peak value. So Vm by root 2, Vm is a peak value, so RMS will be
So
Vm
when
by
the
root 2.
madam, when the question is given like it is some amplitude like 10 volt and what is called
See,
then t with theta.
whenever for the given asked question, the information regarding whether it is RMS or peak has to be known, then it will be mentioned.
Otherwise, it is normal.
Otherwise, by convention, it will be RMS.
Okay.
Or even though if it is peak, so say I told you for any asked parameter, if we have to know specifically it is RMS. Say for example, we are generally it is not given in time domain, but it is directly given in polar representation 10 angle 0. And throughout maybe you are taking calculating some parameters. I think something like we have done in the assignments also. So that time you need not worry about it because throughout we are calculating with this one, whatever here. So
It's
that
by
ratio,
default it's RMS only.
okay. So that will be wherever it is necessary, it will be mentioned.
Okay, ma'am.
So VRMS angle phi. So VRMS is Vm by root 2 angle theta. And then we have, say this is V of t equal to Vm sin omega t is the reference, and I represent this as V1 of t. Then I have another signal V2 of t as Vm sin omega t minus theta. Then we say that V1 of t is with respect to V, the reference signal V of t, which is leading, which is lagging. V1 of t is
V1 leading, V2 lagging.
No, it's not audible.
No, it's audible, madam. V1 is leading and V2 is lagging.
Yeah, V1 of t is leading and V2 is lagging. V1 of t is leading, V of t, and V2 of t is lagging behind V of t. Okay, so I will represent this V2 of t in phasor as Vm by root 2 angle minus theta. Now you have, say, in a circuit V of t is, say, some 10 sine omega t plus 30 degree, and I of t is 5 sine omega t minus 5. Then if you are asked to calculate the impedance, how to calculate the impedance? So phasor representation of V of t will be, sorry, we can't write phasor. Okay, phasor representation of this V of t, it will be 10 by root 2 angle 30 degree. Then
Yes, madam. This is what my question, madam. If the V of t is given 10 sine omega t plus 30, right? So this V is not by default VRMS. It is like VM,
that's
right?
what I told you
Okay.
here. If say for example finding impedance, correct?
If it is in
So
polar form, it is default by VRMS. Otherwise, it's VM actually.
in the I mean time domain expression like this, it is obviously this value is peak value
VM.
Vm.
Okay,
This
VM.
is Im.
Okay, madam.
In the polar representation, this magnitude generally by convention it will be RMS.
So when they mention
Even
is
if
like
you remember, if you go back to your lectures of week 1, initially while introducing this phasor representations in the polar form, the magnitude part of polar form was written in peak by using the peak value. Later towards the end of lecture 1, there
we
we
my
had, if you
yes.
remember, we had emphasized that by convention generally it will be the RMS value.
Okay,
Okay.
madam. Yes, yes.
So here 10 by root 2 angle 30, and this will be 5 by root 2 angle minus 5. So Z will be, magnitude part will be 10 by root 2 by 5 by root 2. So that will be 2. What will be this angle? It will be
35.
35 degree, ma'am.
huh? What
35,
will be
ma'am.
the angle involved in the impedance?
35.
Ma'am,
What is the phase angle in the impedance? Say
35 degree, ma'am.
35 degree. Okay.
35 degree, ma'am.
So 30 minus 5, so that will be 35 degrees. So it will be, Z can be represented as 2 angle 35 degree. And what is the power factor?
Cos 35.
It will be cos 30 or cos 5 or cos 35.
Cos 35.
Cos 35, because it is the cosine of the angle between the voltage and current. So between voltage and current, the angle is 35, or in other words, it is the angle involved in the impedance. So it will be cos 35.
Ma'am, here bar means, ma'am, please 1 second, ma'am.
Vector representation, because this polar, rectangular are vector representations, right? So I have just to denote it as a vector, I have used this symbol. Then what else we have seen? Yeah, coming to the circuits. pure resistive circuit, the voltage and current are in phase. Okay.
Excuse me, ma'am.
V and I in phase.
Hello, ma'am.
One second. Right now it is. Let me see just whether it is streaming out. Okay, no problem. Okay. So in an inductive circuit, it will be, what is the relationship?
Voltage leads current, ma'am.
Voltage leads the current by pure
90.
inductive circuit
By 90
the
degree.
current by 90.
90 degree.
Pure capacitive circuit current leads the voltage by 90 degree. So when you have composite circuit, there will be, depending upon the thing, there will be a phase shift between 0 to 90 degree. Okay, these are the cases for purely resistive inductive or capacitive circuit. So here in a purely resistive circuit, since the voltage and current are in phase, the angle involved in the impedance will be 0. So what will be the power factor?
1, ma'am.
Power factor will be unity in the case of a purely resistive circuit. Then what about this? These two?
0.
0, ma'am.
And for other composite circuits, as I told you, depending upon that angle which lies between 0 and 90 degree, you will have a finite value for this power factor. Then, if you, what about the inductive reactance
Ma'am,
and
why do we call it power factor?
because we have this factor, we have Vi cos phi. This Vi cos phi, this cos phi being 0 only, we get it as simply Vi for a resistive circuit. Otherwise, for an inductive or capacitive circuit, we have the effect of this one. Means we have there is a energy transfer due to this reactive elements, inductor or capacitor in the circuit, and there will be always a power dissipation in the resistive part. So that part of factor of the power, in that way, it is referred as the power factor. This cos phi.
So that means in purely inductive and capacitive
In
circuits,
purely
we
inductive and purely capacitive circuit, the average power will be 0. What is this Vi cos phi? In effect, it is referred as the average power. Average power is otherwise referred as the real power or the power dissipated or power consumed or whatever. So you know that in a pure resistive circuit, this cos phi being 1, it is simply Vi. That means in the DC circuit so far we have seen the power dissipation is Vi or I square R or V square by R or whatever. In the case of purely inductive and purely capacitive, as you mentioned right now, this cos phi being 0, the average power will be 0. Understand the emphasis on it's the average power. That means in one cycle it will be power delivered, in the other cycle it will be getting back, so that the average will be 0. Okay.
okay, sir. Okay, ma'am.
Now, what about these parameters, inductive reactance and capacitive reactance?
XL equal 2 pi FL, X is equal 1 by 2 pi FC, ma'am.
XL equal to omega L, that is equal to 2 pi FL, Then this is 1 by omega c is equal to 1 by 2 pi fc. So you can see that inductive reactance is directly proportional to frequency and capacitive reactance is inversely proportional to frequency. So for capacitive, for very high frequency, what about these values XL and XC?
XL behaves as open circuit.
XL will be very large and XC will be very small. So XL very large means it behaves like a
Open circuit.
the reactance or the resistance offered is very high. That means it acts as a open circuit, and this will be acting as a short circuit. Okay, and vice versa. If we consider the case of low frequency, we can see the contrast happening. Then what else we have seen? Yeah, in so considering this, in general we can write Z as we have the real part, which is the resistive part R. Then depending upon the circuit, we have this J into XL minus XC or XC minus XL. That depends whichever is greater. So this will be the general representation. Then we have seen the resonance condition, series resonance condition. What is that? XL equal to XC. So omega L equal to 1 by omega C. So omega square equal to 1 by LC, or omega is 1 by root LC, or in hertz it is 1 by 2 pi root LC. This is the resonant frequency in radians per second. This is resonant frequency in hertz. So at resonance, you will have, since XL equal to XC, impedance Z will be simply R, because XL minus XC will become 0. That term would vanish. So the circuit will be behaving like a purely resistive circuit, so that the impedance is minimum and hence the current flowing will be maximum. Okay. Then we came to this complex power. So we have average power, reactive power, and apparent power. So average power is Vi cos phi, where phi is the angle involved in the impedance. So this Vi, everything it is Vrms into Irms cos phi. So that is in watts. Then reactive power will be Vrms Irms sin phi. That will be represented in volt ampere reactive. Apparent power will be simply Vrms into Irms, and the unit is volt ampere. So this complex power S is P plus JQ, where P is this is the complex power, S is the complex power, P is the average power, this is the reactive power, and the modulus of S will be root of P square plus Q square That will be the apparent power in volt ampere.
Ma'am, what is the unit that you have written for reactive power?
V, capital A, then small r. To denote reactive, it is small r.
Okay.
Can you go up, please, a little bit for that reactive power? Yeah. Yes, no, I'm okay with it.
Ma'am, for composite network, ma'am, the
Okay.
value of the power factor is from 0 to 1, ma'am, variable from 0 to 1.
Yes.
And phase angle is from 0 to 90 degree, ma'am.
Yes.
Okay, ma'am, thank you.
Ma'am, ma'am.
Ah,
So isn't the phase vary from -90 to +90?
actually, it varies from minus 180 to plus 180. That means these are the things I told you. If you remember in the first class, the angles being measured. This is the 0 degree reference. So angles are measured positive in the anti-clockwise direction. So this will be plus 90, plus 180, plus 270, and here plus 360. So in the other way, clockwise means this will be minus 90, minus 180, minus 270, minus 360. So what you asked right now is the point why, even if you have seen in the assignment the question statement for phase angles, it is wrapped up so that it is confined between plus or minus 180 degree, because uh, plus 235 degree can be written as minus how much?
125.
1
25.
125. So there are different ways of writing this. So if we simply ask for the phase angle, these possibilities are there for entering the values. So that to make it precise, for the answers to be more precise only, we have mentioned that sentence, it is wrapped up so that it is confined between plus or minus 180 degrees. So that you have to put that within that limit.
Ma'am, but when we in case of phase angles,
Uh,
even in a pure inductive and capacitive case, it is just +90 and -90, no ma'am.
in purely inductive and purely capacitive, it is yeah, plus 90 or minus 90.
So in any way, it can't be more than or below than that, no ma'am.
No, you can have a series parallel circuit, correct?
Yes, ma'am.
Compound circuit, series parallel circuit. You can have. You need not. You just need not consider simply RL, RC, etc. You will have something like this R L. Then we have maybe here R C, something like that. Okay.
Yes, ma'am.
There you will see these cases, compound circuits.
Yes, ma'am. So, but in series case, it is not. It is bound between -90 to
Yes.
+90. Yes, ma'am.
So complex power. Then what else? So here, complex power, this P plus JQ. Okay. So that will be okay. Then what else? Then we come to this network theorems in the second week. So we have seen mainly Thevenin and Norton. So always this Thevenin resistance would be equal to the Norton resistance for any linear network. Then how do you calculate if you have computed the parameters, the Thevenin voltage and the Thevenin resistance, then to find out the parameters associated with any load, it can be represented like this: VTH, here it is RTH, then the load being connected, RL, if I am representing it. So you can compute this current through the load or whatever power dissipated, etc., by means of this. So again, source transformation is there. Source transformed version of this Thevenin equivalent circuit will be here. Norton equivalent circuit. That is, you will have a Norton current IN and the Norton resistance RN connected across the load. Now, how to compute this Thevenin voltage and Thevenin resistance? So, for Thevenin resistance, what do? You open circuit this load. You disconnect this load. Then, from the terminals between which this load is connected, you see what is the effective resistance. During that time, you have to deactivate all the independent sources. Okay, dependent sources will remain intact as such. You have to deactivate the independent sources. If there is a voltage source, we have seen from the last term that to deactivate it, we will be replacing it by a short circuit, and if it is a current source, to de-energize it, we will be replacing it with a open circuit. These are for your independent sources: independent voltage source shorted, independent current source open circuited. Then looking from the terminals across which this load is connected, you see what is the effective resistance. That will give you the Thevenin resistance. Then for finding the Thevenin voltage, it is the open circuit voltage. That means across the terminals where this load is connected, you open circuit that, and the open circuit voltage across that terminal will be the Thevenin voltage. Okay. Then in the case of Norton, we short circuit that terminal, we find the short circuit current. Again, finding the Norton resistance will be similar to finding the Thevenin resistance. They both will be equal in magnitude. Then we have seen the case of source transformation, that is any voltage in series with a resistance. Can be source transformed as a current source in parallel to that resistance. The current direction will depend upon the polarity of this I will be V by R, and since why it is shown upwards, because the polarity of this voltage is plus minus. If it was minus plus, the current would be the reverse direction. This will be V by R. Then we have seen the maximum power transfer theorem. So for maximum power, we have seen that the load impedance should be equal to the Thevenin. The load resistance should be equal to the Thevenin resistance. Or if it is a circuit containing reactive elements, instead of referring it as resistive load, it will be a reactive load. So we call it as impedance. So in that case, ZL should be equal to ZTH. And if you have this When you have this AC, what is that? You will have this to be the conjugate of that. That means resistive part will be the same, and this XL should be the source reactive conjugate. Okay, so this is for the maximum power transfer to the load. Then we
Ma'am,
have seen the case.
ma'am, Excel equal to source conjugate. Please explain, ma'am.
This is source resistance. For maximum power, RL is the resistance of the load. The load resistance should be equal to the source resistance for maximum power transfer, and the load reactance should be equal to the conjugate of the source reactance. These are for the AC cases. Okay, so
Ma'am, you're referring to it as a source resistance, whereas just above we mentioned it as R Thevenin and Z Thevenin. Any difference between Z Thevenin and RS and XS?
yeah, this one. How to?
I mean, Z Thevenin star, that's a conjugate you mentioned, right?
Yes.
And is it equal to RS plus JXS?
Yes.
Okay.
Then we have seen the case of dependent sources. Okay, so dependent sources, the representation is within this symbol, a diamond shaped symbol, instead of like this, where we will representing this for voltage source or this for a current source. These are the independent sources. Independent sources, voltage, independent voltage source, independent current source. This will be dependent current source or dependent voltage source.
Ma'am. Ma'am.
Tell me.
Ma'am, regarding that maximum power transfer,
Huh.
why does it work that way, ma'am? Because generally, we have an intuitive that if the resistance is very less, we can get maximum power from the source, right? But the maximum power
You go
transfer,
back to I think I hope this. I mean, why do we say that this load resistance should be equal to the Thevenin resistance or this one source? Actually, here the simple way to what you have asked, someone asked before, is you are asking this RTH and why this RS, right? Actually, we are applying the Thevenin part to the source part only, correct? You
yes,
have
ma'am.
the source side connected to the load side. Source being connected to the load. And we disconnect the load and we apply this Thevenin theorem to the source part, and that source part of the circuit is being transformed as this VTH in series with RTH across the terminals to which this load is being connected. Okay, so actually this RTH is a representation of your source resistance. That's why here it is I have represented as RS. That is the answer for earlier what you have asked. Now for the question, now what you have asked for, you just if you can remember, go back to the lecture. We have in the lecture derived this why we say that this load resistance should be equal to this, because we have seen for maximum thing we take the first derivative and equate to zero, right? Do you remember all those things?
Yes, ma'am. Yes, I know
Uh,
why it works. I mean, the mathematical thing, that's okay. I understand that.
okay.
But I just require some intuitive feel why it works in that way as it is. Because if we take, let's say we have a very high resistance inside in the load side, so the power consumed is very low, right, ma'am? And if
That
we
depends
ready,
upon this one, whether you
yeah,
have voltage source or current source.
yes, ma'am. Let's say the R load is very higher than RTH.
Okay.
Then the power consumed is not maximum, right?
R load is higher.
Then RTH.
Okay.
Then the power consumed is won't be maximum.
That's what. See, that's why we are mentioning what should be this. We represent something like this. It is a variable, right? This
Yes,
arrow
ma'am.
represent this RL taking different value, and by means of through maximum power transfer theorem, what we convey is what should be the value of RL so that the maximum power is being transferred to the load.
Yes, ma'am.
You say
So
you say that some other value during which the maximum power won't take place, maximum power
uh,
transfer won't take place.
yes,
What
ma'am.
should be the value of this load resistance so that maximum power is transferred will be is the thing that is in effect conveyed through this theorem.
Yes, ma'am. Actually, I am asking if the R load is lower than even RTH, is lower even than RTH, why it can't be consuming maximum power?
You are asking R load is greater or lesser?
Lesser, ma'am. If the R load is lesser even than even the RTH, the value of RTH, why can't it consuming maximum power?
This I think I have to take some example and then make you understand. Now, what example
Ma'am,
can I take?
shall I? Ma'am, I have one idea for this.
Okay.
Can I tell, ma'am?
Yeah.
Yeah, Muthu.
Yeah.
Actually, what you are telling was, why can't we take road resistance greater than Thevenin resistance to get more power, right?
No, no. Why can't we take load resistance to be lesser than RTH to get high power,
Yeah.
so that we can have higher current rate?
Ma'am, can I say something, ma'am? Ma'am.
One second. One second. One second. One second. Sorry. One second.
See, if you take like that, it will be like V square by R, right?
Yeah, yeah. So
I guess.
since this depends on both the thing, so we should optimize it in between,
Yeah,
not
we
too
should
low, not too
optimize.
high.
Yeah.
Okay, okay. Yeah.
Yeah. Okay.
Yes, ma'am. Yes.
Yes. Sorry. I had to mean something in between. Tell me. Tell me.
Yes, ma'am. So since it depends both on voltage and current,
Yes.
so we should get some middle point to get the maximum power.
Yes.
Yes. So that would be the reason.
Yeah, but maybe something more effective. How can I let me think and then get back to you with some example or possible, but not
Okay.
today.
Yes,
After
ma'am.
doing
Yes.
the quiz, we can do that. Please remind.
Yes, ma'am. Yes, ma'am. Yes.
Okay, so we were just discussing this dependent sources. Then, uh, then we have seen all these cases. What you have so far learned for the AC case. That means mesh and nodal superposition. All those things you had done in the last term that dealt with AC. Then this new maximum power transfer theorem, Thevenin and Norton also with AC circuits we have dealt in week 3. That's it, right? Correct?
Yes, ma'am.
Okay. So if that is the case, I think to be more effective, I have just selected few problems to discuss with you, numericals that we can do for the rest of the session. And regarding the mock paper that will be getting released either tomorrow night or if it is before that being done, I mean Saturday morning anyway you will get it. Okay, mostly tomorrow. Mock paper,
Yes,
just
ma'am.
go through it. And this assignment, graded assignment solutions are released for 2 and 3, I think. In the portal, it has been uploaded. One is also being given, you will get it shortly. And I hope you have received the other thing I mentioned also. That means week 4 practice assignment, Laplace, correct? You haven't gone through.
Yes, ma'am.
Yes.
What is it, ma'am?
I mean, week 4 practice assignment, some few problems, inverse Laplace transform towards the end. We couldn't discuss during the session, so I told I will be giving it, and that has been released as PDF. Week 4 practice assignment solution I'm talking about. And similarly, week 3, since we couldn't complete some few questions due to lack of time, that was also released as PDF, week 3 practice. So those are in the supplementary contents. You can refer to that. For graded, I told you week 2 and 3 are released. 1 you will be getting it shortly tonight.
Okay, ma'am.
Okay, so let us now do some numericals. Maybe we can just discuss, given the question, discuss how it can be approached or the procedure of doing it. We may need not focus on the numerical values. Okay.
Is calculator allowed, ma'am, in exam or scientific calculator, ma'am?
No,
TCS.
the usual TCS online calculator you will be making use of. That I had already told, because there are some practical constraints for you to make use of this physical scientific calculator. So that you will be using this. Questions will be accordingly. The calculations involved will be, we will take care of. What you can do that, we will be setting it accordingly.
Because we are feeling very difficulty, ma'am. That's why. And also in physical calculator, also, ma'am,
Huh.
we have learned only conversion from polar to rectangular,
No, no,
rectangular.
I told you even going to the complex mode in one of the sessions I have shown you, right? That you have
Yes.
to learn it thoroughly by entering in the complex mode. I mean, for the assignment purpose, I'm talking about making use of the physical scientific calculator. Not only interconversions between rectangular and polar, you can get into the complex mode, so that directly, say for example, some a1 angle b1 plus a2 angle b2. That means adding to polar. Physically, I mean manually, what I suggested was, if it is addition or subtraction, you better write it in rectangular form, correct? And if it is multiplication or division, you better represent it in polar. This was what I have discussed. This is for doing it manually. But a1 angle b1 plus a2 angle b2 directly in complex mode you can add. Similarly, rectangular form, division or multiplication, all these things as such you can do. You just go through and learn it, or else we a separate session we can do it later, after the quiz, not before the quiz, so that assignment purpose you will be definitely making it fast. You need not at each step convert this rectangle to polar or polar to rectangular as it is required. Directly feed in these representations, whatever is the operation to be done, addition or something like that, you can get it directly. Learn that all these are available in your the scientific calculator. So in this circuit, how do you calculate the equivalent impedance? Tell me. Just tell me how to. I mean, the expression.
Ma'am, as per diagram, ma'am, we have to make series calculation of 2 ohms and minus J4 ohms.
Yeah, you can just tell me which are in series, which are in parallel. How to just do go about it.
Ma'am, 2 ohms and minus J4 ohms are in series, ma'am. We had
Okay.
to add, ma'am. That is 2 minus J4 and
This is 1 plus
1
J3.
1 plus J3, and these are parallel, ma'am. Parallel calculation we have to do, ma'am.
Okay. So this set 1, if I represent it as this 5 plus J10. Set 2, if I represent it as 2 minus J4. And set 3 as 1 plus J3. Then set equivalent will be set 1 plus uh, set 2 parallel set 3. So that will be set 1 plus set 2 set 3 by set 2 plus set 3. So this is just a piece of thing where that you may require for doing the numericals. Okay, now here. So in the series parallel circuit here, the effective value of the voltage across the parallel parts is 50 volts. Okay. Determine the magnitude of this V.
Ma'am, this 50 volt is a magnitude or 50 phase?
Magnitude. Magnitude. So how do we go about this?
Ma'am, we have to calculate the equivalent impedance of 10 ohms, J30 ohms, and J3 ohms, ma'am. Then 50 volt divided by this equivalent impedance will give the current, I think. Current to the parallel path, ma'am.
So in effect, what you have is this is the applied voltage. We need to calculate the magnitude of that. So we have this as a compound circuit where you have this is a 8.5 angle 30. This is an impedance set, and you have here an impedance which accounts for this parallel branch. So you have this these two branches in parallel, that is in series with this. So the effective impedance will be what? The total impedance will be this 8.5 angle 30, that is in series with these two in parallel. So how can I represent this one? J3 is in polar, it is 3 angle 90. J represents plus J represents a phase of plus 90, and the magnitude is this 3. So 3 angle 90, that is in parallel to this 10 plus J3. So into 10 plus J3 divided by, that is R1 R2 by, or Z1 Z2 by Z1 plus Z2. So 3 angle 90 plus 10 plus J3. This will be the total impedance, and if you try to calculate this, you will get it around 'okay. So these things you can do it as such. We are just focusing on the procedure. Then uh, this V will be simply this I into set T. So how to calculate this I will be we can calculate this I by this given data. 50 volt is being given across this parallel branch. So the current in the, since we know the voltage across the parallel branch, we can calculate the currents flowing in each of these parallel branches, and sum of those currents will be the total current, this I. Correct? Am I right? You know this impedance, this branch impedance, which is J3. This is 10 plus J30, and across which it is 50 volt. So this 50 volt divided by this impedance will be the current flowing through this parallel branch. Again, 50 by this will give you the current flowing through this branch. These two currents summed up will give you the total current I. Then we have the total impedance. So I into this total current into total impedance will give you the applied voltage V. So current in the J3 ohm branch, we can calculate it as 50 divided by 3. Correct?
Shouldn't it be J3?
We are calculating the magnitude. Yeah. Let me write it as magnitude. Magnitude of the current in the J3 ohm branch is 50 by 3. Is it fine if I write it as magnitude? Clear?
Yeah. Yep. But it will have negative sign, so direction of
Yes.
current will be different, right?
Where do you have negative side?
I mean, since J comes in the denominator, and if I take it in the, means rationalize it, negative sign will appear, right?
No.
Okay.
I too think the same.
Anyway, if you are taking magnitude, right? No, magnitude.
It's like r squared, square root of r squared plus xl squared. So that j will not be there. So it is only the component inside is there, not the
Yeah.
j component.
So magnitude of the current in this 10 plus J30 ohm branch will be similarly this 50 divided by this square root of this 10 square plus 30 square. So this if I am taking it as I1, this if I am taking it as I2, then I1 plus I2 will be the total current. Then V will be this I total into set total. Set total we have just now computed. So with that you can calculate the magnitude of V. So Let me just write here this values. You can calculate later when you refer it offline for future learning. Also, you can do it as homework and check with the answers. We are just discussing here right now.
Ma'am,
Yes.
ma'am, while calculating the magnitude, shouldn't we calculate it at the last step?
Last step means what do you mean?
Um, the initially we calculated the current through J30, right?
J3.
J3.
Ah.
So at that time, we should keep the negative and
See, don't
after.
get confused. The question is we are asked to calculate the magnitude of the applied voltage V,
Yes, ma'am.
so that we
But
are throughout dealing with the finding with the magnitude of these. So you need not worry about this. Actually, you people are worried about representing it as complex. So that you are telling that this should be 50 by J3 or something like that, right?
yes, ma'am. So if we keep this way, we will be
Ah.
having minus 50 by 3. And if we add this with the other current, so we should be adding it vector sum, right? So then the magnitude will differ.
How do we say, see, 50 by J3, this 1 by J, if you write it as, that will be minus 50 J by 3, correct?
Yes, ma'am.
Again, if you take the magnitude, what will be that? 50 by 3 only.
No, ma'am. So instead of taking magnitude at this step itself, maybe we take the next current on the next branch and do the vector sum, and after that we can take the magnitude. No, ma'am. Then the magnitude may differ, right?
I don't understand that point. If you take towards the end, what is that?
Uh, no, ma'am. So the current through the rightmost branch also have some phase, right?
Correct.
The J component.
Correct.
Yeah. So so the current through that whole branches will be the vector sum. And what if we calculate the magnitude at the last step?
You just try it out and see. I actually really don't understand your point. Maybe with this answer, you just try it out what you are
Okay,
asking,
ma'am.
and then I
Yes,
don't
ma'am.
understand your point.
Yes, ma'am. So yes, ma'am. Okay.
Set total magnitude will be 10.21. Okay, next question. So for the series parallel circuit, um, you have this 1 plus J2 ohm being connected in series to this parallel combination, where you have in each of these branches it is 3 ohm and J4 ohm in series. Then across which this 10 plus J20 volt is being applied. So you are asked to determine the total impedance between the terminals A and B and state whether it is inductive or capacitive. Okay, that impedance is inductive or capacitive. Then determine the voltage across the parallel branch and the phase angle.
Ma'am, what is the value of inductors, ma'am, in parallel branches, ma'am? J4 ohms and
J4. Both are J4.
J-
So here you can see that this parallel branches, each of these parallel branches are 3 plus J4. What do you have here? 1 plus J2. So 3 plus J4 parallel 3 plus J4. That will be 1.5 plus J2. Then set total will be this 1 plus J2 in series with this 1.5 plus J2. So this is of the form R plus JXL form. So the impedance is inductive or capacitive.
inductive, ma'am.
Inductive.
So it is inductive. Then you are asked to calculate the what is that? The voltage across the parallel branch. So with this we can calculate the total current. Total current will be the applied voltage, the source voltage by the total impedance. So that will be 10 plus J20 divided by 2.5 plus J4. So you will get it like this: 4.74 angle, 5.44 degree. So this will be the total current. So what is this polar form of 10 plus D20? Three point four three.
63.43 angle.
Okay. So source voltage this 20 plus J how much? Sorry, 10 plus J20. Plus J20, that will be 22.36 angle 63.43. That means the angle involved in this voltage is this 63.43, so that the current is this much. So phase angle theta will be now voltage across the parallel branch will be what? The current flowing into that impedance. That impedance is actually what how much it was 1.5 plus J2. So the voltage across the parallel branch will be what was the current 4.74. So 4.74 angle 5.44 into 1.5 plus J2.
Ma'am? Excuse me, ma'am.
Is there any doubts regarding this week 4 graded solutions? I mean, answer key, since you have submitted it yesterday. To just check with your scores, I'm asking. You have submitted your week 4 last night, correct?
Yes, ma'am.
Yes, ma'am.
And once you have submitted, you would have seen the answer key. Anyone having any doubts or something to point out in that? Have you gone through the answer key? Is it fine? Because so far I haven't seen anything in the discourse.
Ma'am? Hello, ma'am.
Yes.
Yes, ma'am. The question, the second one, the which we did before. Yeah, I'm getting as 18.25.
Which one?
Almost.
Here you are telling
Yes, ma'am. Yes, almost same only.
18.25.
Yes, ma'am.
Oh, you were telling with your method. Right.
Yes,
Okay,
ma'am.
okay.
Uh,
And now it's clear what you have asked.
sorry, ma'am. 18.17, ma'am.
That's fine.
Yes, ma'am. Yes, almost same. Yes. So it would be similar even if the one of the branches had a capacitor also, ma'am.
Actually, can you just tell me your point again? If one of the branches is
Capacitor contains a capacitor. Because
okay.
one branch will have a leading current and other will have a lagging current.
Here also it is one of the thing inductor, right?
No, I mean two of the branches have a lagging current.
Correct. Anyway, we will be computing that vector sum. Correct.
Yes, ma'am. Yes.
Uh,
So it won't make any difference.
hmm.
Okay. And ma'am, for the activity questions of week 1, is there any answer key available in portal or any videos where you have done the solutions?
You are asking for week 1 activity which was released to you already.
Yes, ma'am. Yes.
We had already discussed in the live session.
Okay. So I may go through this.
Other than that, I mean, just like for your assignment, nothing is being shared in the portal for the solutions for the activity because it is discussed in the live session.
Okay.
Maybe you can refer to that YouTube link of that session.
Yes, ma'am. Yes.
Just one doubt. Whenever the voltage will be given in time domain,
Okay.
do we need to convert in the RMS when we are shifting to the complex or polar form? Then do the calculation part.
Yeah, for polar form, you take the RMS value.
And for complex also.
And for
And
complex.
because as per the lecture, professor lecture, only in the time domain it is given in the normal form. In other form, you have to take RMS. Is it right that?
That's what we discussed. The magnitude part of the polar form is by convention RMS value.
Okay, okay. So I'm asking in the exam if there are some question like that, so we have to proceed in the same way, correct?
That's what we discussed sometime before, where explicitly that you need, say, for example, um, uh, this is the point whether you people understood what I meant. I don't know. The thing is, say, for example, if you're taking ratio of both taken peak values or RMS value, it will be the same, right? So that in those cases it doesn't matter that you need not know about it, but where it is explicitly required that whether that is RMS or peak, that will be given, I mean mentioned.
Okay, understood. Yeah.
So for this series parallel circuit, uh, this is set A, this is set B, and this is set C, and the values are also being marked, and the voltage across the circuit is 100 plus J0. Find the current IA, IB, and the phase angle between them. So it's just like you do it in the case of DC. So what here you have the set total will be set C plus set A set B by set A plus set B. Set A and set B are in parallel. So set A set B by set A plus set B. That is in series with this set C. So that will give you the total impedance. So that you can calculate. You will get it as with that you can calculate the total current. That will be the supplied voltage 100 plus J0 divided by this total impedance. So the meaning is the current lags behind the voltage by
is 10.34 na ma'am.
minus 10.34. Voltage by 10.34 because the angle involved in the applied voltage is 0 because 100 plus J0, that is 100 angle 0. Earlier we had a angle involved in the applied voltage here 10 plus J20, so that angle was the 63.43, so that difference was the phase angle. So here um, this is the case. Now just like we do in DC circuits, we can calculate the current in the parallel branch. So IA and IB are asked. So IA, it would be total current into the branch parallel to that, that is set B by set A plus set B. So that will give you. So you can later do this and cross-check the answers. You can make use of for your additional practice. Okay, maybe right now for the quiz or later for your NSEM also. That's why I'm giving you the final answers also. But I may not be solving it here because we had already done sufficient number of things. Maybe you can, if you have doubts, I will clarify. So the current in this one will be set A by set A plus set B. These are by current division rule. So angle between so that was minus 50.04. This was plus 22.32. So the angle between them will be the sum of two. So that will be 72.36. That's question number 4. Okay. Now 5. A series circuit consisting of two pure components has the following voltage and current expressions. Find the components in the circuit. We had done similar question in the assignment. So from the given expression for the current and voltage, you can see that the phase angle between them is 45 degree, which is leading. Current is leading.
Current is
So angle between V and I will be 45 degree. I leads V. So since the current leads the voltage, we understand that the components are resistor and capacitor. Now we need to find out the.
Madam, is this recorded actually?
Actually, I don't know, some issue with the live streaming, but I am recording it in the Gmeet. Maybe that I can share with you.
Thank you, madam.
I am recording it. Recording is going on.
Okay, madam, because that will be help us for some
Yeah,
revision.
sure. That I have taken care of, but I don't know what happened with the streaming today.
Okay, madam.
I mean the question, ma'am, after pure components, ma'am, what is written, ma'am?
Where?
In the question-
Find the
question
components in the circuit.
The com-
Find the components in the circuit.
Okay.
So here we understand that since the current leads the voltage, that a reactive element is capacitor. So resistor and capacitor. Since it is mentioned that two pure components. Okay. So tan this phase angle, which is 45, tan 45 will be 1 by omega CR. So 1 is your tan 45, so 1 by omega CR is 1. Therefore 1 by omega C is your R.
Ma'am, the voltage given in the question is source voltage or capacitive voltage?
Which one?
Ma'am, in this question.
The source voltage, applied voltage.
Oh.
కృష్ణమూర్తి నిన్న ఒక సర్వెంట్ గారు మాట్లాడతావు తిట్టే మరి நிறைய பேசுறா நீ வெளியே போய் பேசிட்டு வீட்டுக்குள்ள வந்து
అక్కడ బయట ఇక్కడ కాదు ఇక్కడ మాట్లాడలేదుగా వాడికి రానే రాడు వాడు గేట్ కూడా వచ్చి అచ్చా ఓకే పంపించేస్తాను ఏంటంటే నోరు జాస్తి మాట్లాడు వాడు
Can you please mute from your side?
అంతక నోరు జాస్తి మాట్లాడారు అట్లా పంపించేస్తాను వాడు పెద్ద ఇది వచ్చింటాడు 4 చిన్న పని
Sir, can you just mute from your side?
ఒక చిన్న పని దానికేమో బిల్డప్ చేసుకుని మాట దాన్ని ఎత్తిపోయి వాడు డాక్టర్ అంటాడు వాడు ఎందుకు పనికి రాడు డాక్టర్ సరి మూల మంగిపోయింది మగ్గం చేసేవాళ్ళు లాజికల్ థింక్ చేయండి.
Ma'am, you can mute from your side. The icon after clicking the icon.
Please scroll up.
Hello.
Hello?
Yeah, this question I just wanted to ask. You cannot do a division by current and get the complex number, and the real part will be the resistor.
One second, tell me.
What I'm saying, the
This
voltage and
question?
current. This question can be solved in this way also. Since the voltage and current is given,
Okay.
we can find the total impedance, and in the impedance, the real part will be the resistor, and the conjugate complex part, imaginary part will be the capacitance.
Reactive part will be the XC, correct.
Yeah, so that way also it can work, huh?
Yeah, correct.
Okay.
Find the average power delivered by the voltage source. So if you consider this node and I consider that node voltage V, what we can do is Vx will be V by 1 plus V3. Okay. Okay. So applying KCL at the node, we can write it as this 10 cos 50t is
Ma'am, can you tell me the voltage source power? 100 cos 50?
50t, 100 cos 50t.
50 V. 50.
So that is 100 angle 0. So V minus 100 angle 0. Here you take cosine as the reference, okay? So V minus 100 angle 0 by 2 plus V by 1 plus J3 plus V minus 50 Vx by minus J4 equal to 0. So this Vx will be 1 ohm into Ix. So Ix is V by 1 plus J3. So that will be V by 1 plus J3. So substituting for Vx in the above equation, you will get V as 14.705 angle 157.5. So this current flowing will be V minus 100 angle 0 by 2. That will result as 43.29 angle 3.7. Current flowing out of the source. With that you will get power delivered by the source as this 100 into 43.29 by 2. Okay, by applying this KCL at this node, I have written the equation here, equation 1. And what we are asked is the average power delivered by the voltage source, this 100 angle 0 voltage source. So for that we need to calculate this current. So if we know the node voltage V, then this V minus 100 angle 0 by 2 will give you that current. So that will be in this direction. Since we have taken V minus, that will be in this direction. So in effect, that will be the power delivered by this, and that will result in this value. You can just go through.
Now, once again, can you show that solution?
Please scroll up, ma'am.
Yes, ma'am, scroll up. A bit down, ma'am.
1 second.
Still down, ma'am. Yes, ma'am. That's it, ma'am. Thank you.
Ma'am, after V, ma'am, please show, ma'am. 14.705.
One second, just give me 2 minutes. I have got a call. Yeah, tell me. Find the average power delivered by the dependent current source. So if we again consider this as V applying KCL at this node, I can write it as V minus 20 angle 0 by 10 plus V by 20 equal to 0.5 V1. So V1 equal to 20 angle 0 minus V. Equal to 18.46 angle 0 and V1 equal to 1.54 angle 0. So average power delivered will be Vm by root 2 Im by root 2 cos theta. So that will be last problem. One second. Let me take that question. Okay. So this question. So here we have, while applying Thevenin theorem, here we have a dependent source actually. So while trying to calculate the Thevenin resistance, you may open circuit that 5 ampere, which is a independent current source, but you have to keep this 2Vx dependent source intact. So how will you do? We generally, in the presence of a dependent source, we excite the network with a voltage source, or we apply a current source also. We have seen the test current, etc., even in the lecture. So this one particular example, I can show it for you. With that, we can wind up. Okay. So one better way of doing it is using mesh analysis. So I consider the mesh currents I1, I2 and I3 for the 3 loops. So for the mesh 1, these are the equations for this mesh 3. It would be minus 2Vx plus 2 into I1 minus I2 equal to 0 in this mesh. Minus 2Vx plus 2 into, okay, so this will be I1. Sorry, I had taken the other way. So I1, I2, I3. So mesh 1 I have minus 2Vx plus 2 into I1 minus I2 equal to 0. That is the thing, this should be the label. Okay, fine, no problem. Or we have Vx equal to I1 minus I2. Then 4 I2 plus 2 into I2 minus I1 plus 6 into I2 minus I3 equal to 0. Six into I3 minus I2 plus 2 I3 plus 1 equal to 0. Correct? 6. Okay.
Ma'am, this is for mesh 3, right? This equation?
Which one? These are for mesh 2 and 3. Mesh 1 is here. These are for mesh 2 and 3. Mesh 2 is 4I2. Mesh 2 is here.
Yeah, so
4.
in mesh 2, 4 ohm resistance will have two currents flowing through it, right? I2 and I3.
I2.
4 ohm resistance.
You have a resistance in parallel to the current source, correct? So yeah, you can apply KVL. Let me just complete it. But the thing is, you have to apply the test current source for the dependent current source. Either you can simply apply a test voltage source of 1 volt, or you apply the test current source.
Ma'am?
So that will be RTH will be then, if you apply test voltage source of 1 volt, then RTH will be the current flowing through that test voltage source. If it is IE, then 1 volt 1 by I naught will be your RTH. So this I can complete it and share it with you. Take care when you have dependent sources in the circuit. Okay, so with this question I am winding it up. So one thing that you need to take care of is, again, just like what I have told you in the last term, please take care of the calculations. That is the place where you go wrong in general. Fine.
Ma'am,
Tell me.
ma'am, in the last question,
Yes.
could you
1 second.
go down, please?
Last question.
Yes, ma'am. So, is it I3 is equal to 5?
I3 equal to 5. Correct. This I will just, with that test current source or voltage source, let me see, and I will just complete this and share it with you. I3, as of now, what I have written, I have considered this as I3, so that will be 5 ampere.
Yes,
Okay.
ma'am. Likewise, for mesh 2, 6 ohm, the current flowing through it will only be I2, no, ma'am?
I2.
But the expression is different.
Yeah, that's why I need to check. That's why I told you I will just go through and then share it with you.
Yes, ma'am. 4 and 6 are replaced, are interchanged, I think.
Correct. Okay.
And yes, ma'am. But so far we haven't come across these kind of questions, I think, ma'am, because the Vx will always be in the rightmost side, so that we can add a voltage.
That's why I typically have chosen this.
Yes, ma'am.
For the revision session, these were picky questions. I took it just for making you. So this I will just go through where I have gone wrong, and then I will share it with you. So mock, as I have already mentioned, will be released to you tomorrow.
Yes,
Okay.
ma'am. So, ma'am, this last kind of question, can we express this kind also in quiz 1?
Maybe.
Yes, ma'am. So if you could share the answers soon, it would be
Yeah.
better. Yeah.
Hello, ma'am.
Just tell me.
Ma'am, if you can share this PDF, even that will be more helpful for us, ma'am.
Which one? Which one?
This PDF, whatever you have written right now.
Here, this one for the revision session. You are telling.
Yes, ma'am.
Yeah.
Yes, ma'am. Thank you.
Okay. So all the best. Do well.
Thank you.
Okay. Thank you.
Thank you, ma'am.
Yeah,
Thank
we
Thank
you.
you,
will
ma'am.
see again on Monday. Thank you. Do well. All the best for all the courses.
Yes. Thank you, ma'am. Yes.
Yeah, Venkatesh Subhash, you want to ask something? Yeah, no, okay. Fine.
Thank you, ma'am.
Thank you.